Okay, for this video, we're going through the 2015 paper. Okay, question 1. In cold countries, people wear coats that are designed to reduce the rate at which thermal energy is lost from their bodies, right? They don't want to lose too much thermal energy, so they wear coats. Material for some coats is made from a thin layer of thin strips of silver. So when you see silver, you think of radiation, right? Okay, and silver is a poor absorber and emitter of thermal radiation. Okay, but later on we have to see which whether is it absorbing or emitting. Okay, so we have thin strips of silver color plastic. Okay, why plastic? Because plastic is a poor thermal conductor. Okay, so you must be very sensitive to all these words. Between two layers of fabric, so this is my first layer, second layer of fabric, then I have the silver colored plastic. So the plastic strips trap small pockets of air. So air is a poor thermal conductor. So the design is that the layer of silver colored plastic strips reduces loss of thermal energy by conduction, convection and radiation. So we have to explain for these three processes. Now let's take a look at the answers. Okay, so we have to actually identify the processes. So for conduction, we say that plastic is a poor conductor of heat, but we try not to use that now. We say that it's a poor thermal conductor. Okay, so this will suffice. This is a poor thermal conductor. And also the trapped air is also very poor thermal conductor. Okay, so air is also a poor thermal conductor. So this reduces the rate of thermal energy lost from a body to the surrounding by conduction. So basically these 2 points will get you your 2 marks. So if you see this, the mark scheme says 2 marks, that means there must be 2 points. The first one is plastic, second one is the trapped air. So how about for convection? Let's take a look. Okay, so for convection, it is 1 mark. Since the heated air is separated into pockets of trapped air, right? If you look at the design here, the air is found in all these empty spaces there. Okay, and because the heated air is separated into pockets of trapped air, so this has something to do with like your polystyrene. Okay, your polystyrene also has many small pockets of air. So what's the purpose of the air? We have mentioned above, air is a poor thermal conductor. Plus, if I have them in small pockets, that means they are not able to come into contact with other pockets, right? So the pockets of trapped air, they will be unable to flow freely and not in contact with the surrounding cold air. Okay, so therefore there will be no convection current form. Okay, so this is the reason why this layer of silver color plastic strips that traps the air reduces convection. Okay, so the Marcus report say that need to explain why convection cannot occur, but you don't need to explain the process of convection because they are only asking for the reason. The last one is actually on radiation. Let's take a look at the answer. I think in my lesson I did tell you all before that usually radiation, we don't talk about the absorbing and emitting in the same statement. But for this case, there's actually 2 parts to it. Okay, now silver surfaces, they are poor thermal absorber and poor emitter. So the silver surface of the plastic strips are poor absorber, and actually this is absorbing from the human body because in the winter, cold country, the body is actually hotter than the surrounding, right? So these silver surfaces will absorb the thermal energy at a slower rate. Okay, and also then they will emit at a lower rate to the colder surrounding. Okay, so in this case we need to mention that based on the context, the silver strips are poor absorber. Okay, qualify it by saying that it's from the human body, and poor emitters, it is emitting to the colder surrounding is a poor emitter. Okay, let's take a look at question 2. When an aircraft is about to take off, it accelerates at a rate of 3 meters per second square. So this is A, and this is a constant value. For how long? For 25 seconds. So this is my T. Average mass is 1.25 times 10 to the power of 5. So this is my mass, M. Okay, then they ask us to calculate for the aircraft the average accelerating force. So whenever there's a force or whenever there's acceleration, there'll be force and vice versa. So how do we calculate that? We use F net equals to MA, because this acceleration was brought on by this accelerating force. So we just take the mass, 1.2 times 10 to the power of 5 multiplied by 3. We will get a value of 360,000 newtons, and that will get you your 2 marks. So the speed after 25 seconds initially was about to take off. That means it was at rest. Okay, after 25 seconds it will have a certain speed, so we have to use A equals to V minus U over T. So the A is actually 3, the final speed unknown, U is 0, time is a duration of 25 seconds. Therefore the final velocity is 25 times 3 equals to 75 meter per second. Okay, so what's the minimum vertical force for takeoff? In order for it to take off, then it must be lifted off the ground, right? So we actually have to calculate the weight of the aircraft, and you see they actually give us the gravitational field strength, so that should tell us, and it's a 1 mark question. So W equals to mg. The mass is 1.2 times 10 to the power of 5 multiplied by gravitational field strength. So I'll get 1.2 times 10 to the power of 6 Newton. Okay, yeah. Okay, question 3. EM waves have many applications. Complete 3.1 to state the region of the EM spectrum used for each of the application. So mobile phones, a common mistake will be radio waves, but it's actually microwaves. Okay, sunbathe will be ultraviolet. Okay, sorry, I think I should spell it out. So don't just use short form UV, spell it out, ultraviolet. So remote control is infrared. Satellite TV will actually also be microwaves, because they didn't say that you can only use fill in the same unique answer for each box. So 1 mark for each correct answer. State which type of EM wave that you have named in 3.1 that has the greatest frequency. So you have to recall this. So based on your answer, ultraviolet seems to have the highest frequency. Okay, just to make sure that you all remember, gamma has the highest frequency. Okay, radio wave has the lowest frequency. And since they all have the same speed, which is speed of light in vacuum, is c, so we use v equals to f lambda, right? If the v is the same for all waves, and if I have highest frequency for here, that means my lambda, my wavelength, will be the lowest. So it will have the lowest wavelength. Okay. Okay, then question 4 is about pressure. Okay, so cross-sectional area of the U-tube is 3 cm square. So we need to take note of that. Density of liquid A is 1.2 grams per cm cube, which is good because they give us everything in cm square. See, cm, cm, cm cube, cm square. Okay, so later on we don't need to convert anything, but I would just like to take note that this is rho A, which is density of A is 1.2 grams per cm cube. Because the point X is at the junction here between liquids A and B, point Y is the same horizontal level, that means X and Y is here. Okay, in liquid B, surface of liquid A is 15 cm, this one I take note. Above point X, the surface of liquid B is 24 cm. So they want us to calculate the mass of liquid A. Now mass, I'm given density, so of course I'll use density equals to mass over volume. So now I have to find mass of liquid A, so I have to use MA. over VA equals to density of A, which I'm given this. This is unknown, so now I have to find my volume of A. Okay, and because I have a cross-sectional area AA, I have the height HA, so density is 1.2 grams per cm cube. I just write the units here. Mass of A is unknown. Volume of A is actually cross-sectional area of A multiplied by height of A of the liquid. Okay, so in the end, I'll just bring this over. Okay, I'll bring this over. Okay, I'll leave MA on this side. So I need to multiply by AA. AA is actually 3 cm square. HA is actually 15 cm. Okay, so you see the units actually cancel out nicely, leaving behind the grams, which is the mass. Okay, unit for mass is grams. So I'll get a value of 1.2 times 3 times 15. Okay, let me calculate that. I will get 54 grams. Okay, so this is my answer, 54 grams. Now, pressure at X due to liquid at A. So you only learn pressure equals to force over area. Okay, so why did they ask us to calculate the mass? Okay, because this force is actually due to the weight of A acting on this cross-sectional area on A, right? So weight of A is actually M of A multiplied by G AA. I hope you know how why I write all this, because the subscript actually tells us that it's belonging to A. But mass of A, if I were to use W equals to mg, right, this is actually a SI unit. So if you are not careful, you will not change your mass to kg. You will still leave it as grams, which is incorrect. So you need to change it to kg. So I need to take 54 over 1000 times 10, which is the gravitational field strength. So this is actually the trick here, to convert it into kg, which some candidates, I believe, doesn't do that. So cross-sectional area of A, and you see they are looking for Newton per cm square. So for my area of A, cross-sectional area is already given in 3 cm square. So I don't need to change anything. I just leave it as 3 cm square, because the answer wants me to leave it in Newton per cm square. And of course, W, the unit is newtons. So this thing, whole thing here, will give me the unit of Newton. So I'll have 540 over 1000. This whole thing divided by 3. And I'll get answer of 0.18. So answer for this is 0.18. Okay, please check that you know how to do. If you have made a mistake of not converting your grams to kg, please take note. Some formulas are requiring you to leave everything in SI unit. Okay, so part B, the pressure due to liquid B at point Y is the same as the pressure due to liquid A at point X. That means this 0.18 will be the pressure at B. Okay, it's also 0.18 Newton per cm square. So now we need to reverse this whole thing, calculate the density of liquid B. Okay, so pressure equals to force over area, but now it's force B over area of B. Okay, what is force B? Force B is actually weight of B over area of B equals to mass of B times G over area of B. Now, what is the mass of B then? Mass of B is equals to, if I use density equals to mass over volume, mass will then be density times volume. So I need to use density of B multiplied by volume of B. Okay, so do we have anything? We have the height of B, right? So this is liquid B, right? Liquid B. We have the cross-sectional area of B, AB. We have height B. So we can actually find the volume of B to be AB multiplied by HB. Okay, so I'll just do the calculation here and transfer below. So area of B is the same, cross-sectional area, so it's 3 multiplied by the height of 24, so I get 72 cm cube. Okay, So I'm going to bring it to here. Okay, so my mass is going to be density of B multiplied by volume. Okay, it looks like a bit messy now. Okay, because you're so I'm going to try substituting everything inside. So start with pressure equals to MB, mass of B times G over AB. Okay, then I have the mass of B as density of B. So take note, this is pressure. Yeah, I just put pressure. Volume, I have it. Volume was 72. Cross-sectional area, oh, I still need to multiply by my G here. Yes, my G. Cross-sectional area is 3. Okay, so my pressure is the same, right? So I get 0.18 here equals to density of B. This is what I want to find. And I will have this as 10. So I will have 720 over 3. Okay, but my mass, okay, it can be quite messy now. Okay, my G, MB. Okay, sorry, there's a bit of confusion because of the units. For MB, right, you actually need to divide by 1000 because just now, when we use the density of A and the volume of A, it gives us things like grams and cm cube. But if you were to calculate the force, right, for the force, we actually need it in SI unit. So the mass, we actually need to divide by 1000. That means this whole thing, in the end, must divide by 1000 as well. If not, I will not be able to get, okay, let's try it. So I will get density of B equals to, this is divided by 1000, so I will shift my 1000 over here. So in the end, my calculation, I will get, okay, in the end, I'll get 0.75 grams per cm cube because I have converted it to, yeah. Okay, so the final answer is actually 0.75 grams per cm cube. All right. Okay, now question 5. Archer fires an arrow vertically upwards into the air, as shown in figure 5.1. The string of the bow is pulled back a distance of 60 cm. So this is a distance. So I may just want to convert it to meters, because this may be a energy problem. So everything needs to be in SI unit. Average force of 125 Newton. The arrow has a mass of 0.18 kg in SI unit, so it's okay. Energy transferred to the arrow when the string is released is 75%. So initially, if I have 10 joules stored in a bow, then 75% will become 7.5 joules that is transferred to the string. Okay, and given G is 10 Newton per kg, ignoring any effects of friction, calculate the work done in pulling back the string of the bow. So work done is equals to force times distance moved in the direction of the force. The force is 125, and the distance that is being pulled is 0.60 meters. So that's why I need to convert it to SI unit. So 125 times 0.6 is actually 75 joules. Now the speed with which the arrow leaves the bow. So this is the work done on the bow. And remember, we are only giving 75%, or 75% of the energy is then transferred to the arrow. So the energy transferred to arrow equals to 75 over 100 times 75. So it's equal to 56.25 joules. I'll just leave it as this value. So this energy in the bowl will then transfer this energy to the kinetic store of the arrow. Okay, kinetic store. So KE equals to half mv square. So the KE is 56.25 equals to half. The mass is 0.18 SI unit already. Make sure it's V square. So when I do my calculation, V will be 25 meter per second. Okay, so what's the maximum height reached by the arrow? So this is the amount of energy that's being transferred to the arrow. And if let's say we ignore any effects of friction and air resistance, so by principle of conservation of energy, the KE will be transferred to the gravitational potential store of the arrow. Okay, so 56.25 equals to GPE's formula mgh, right? Because they want us to find the maximum height. So 56.25 equals to 0.18 times 10, then h. So therefore my h is 31.3 meters. Okay. Okay, question 6, you see pivot, that means you know it's a moments question. So she applies a vertical force of 110 Newton on the pedal. As she travels along, the pedal moves through a circle of radius 8 cm. So this whole thing is 8 cm. For the pedal in the position shown in figure 6.1, line of action of the force F is 5 cm away. So this is the perpendicular distance. Okay, so calculate the moment of force F about the pivot. So this is easy. Moment equals to force times perpendicular distance. Okay, and they want us to leave the answer in Newton cm. So there's no need to change the perpendicular distance to meters. Okay, so the force is 110 multiplied by 5. So I get 550 Newton cm. Please do not leave it in joules, yeah? Okay, then the pedal moves from position A to B. So A was here. It moves from A to B, right? So explain why the force applied at A will have a different effect from the same force applied at B. So it's still a moment question. So they are asking us what is the moment that is produced. Okay, so let me show you the answer. Okay, at A, the perpendicular distance between the line of action of the force and the pivot is 0. Therefore, no moment of force is produced. Is that true? Let's take a look. At A, if the pedal is here and she applies a force here, it will pass through the pivot. So therefore, the perpendicular distance is 0. Therefore, there's no moment, right? Because moment equals to force times perpendicular distance. If my perpendicular distance is 0, therefore, my moment will be 0. Okay? But when the force is applied at B, the perpendicular distance between the line of action of the force and the pivot is the greatest, which is at 8 cm, right? In between, over here, that was our calculation. The perpendicular distance is 5 cm. But when it's applied at B, the pedal is at B. This is a force, let's say, and this will then be the entire radius, which is 8 cm. And again, moment equals to force times perpendicular distance. So the force is the same, but the perpendicular distance will be the greatest. Therefore, there will be maximum moment of force produced. Okay, so this is what they suggest us to talk about. Discuss using the term perpendicular distance. So these are important keywords between the line of action of the force and the pivot. So not just perpendicular distance. It's your last exam, so make sure you write everything explicitly. So it's the perpendicular distance between the line of action of the force and the pivot. So please memorize how to use this term. Okay, so this question is not about principle of moment, so the vertical force does not vary because they didn't say anything about changing the force. So these are what some candidates actually made mistakes. Okay, periscope here is not tested out of our syllabus because they talk about critical angle, no longer in our syllabus. Now we go to this question 8. 3 resistors X, Y, and Z are connected in parallel. So some, same. So over here will also be 6 volt, right? Okay, so the total effective resistance of the circuit is 0.75 ohm. The current in resistor X is 3 ampere. So this is the I. and the current in resistor Y is 1 ampere. So I call this IY and this is IX. Calculate the current in the battery. So the total effective resistance, so this is IFF, that means 6 volts. I can replace it with this effective resistance of 0.75 ohm, right? So this can be replaced by this 6 volt. So the current in the battery, so V equals to IR. The V is 6, the I is unknown, R is 0.75. Therefore, the answer will be 8 ampere. Okay, remember to leave it in 2 or 3 SF. Now, they want us to calculate the current in resistor Z. Okay, sum. The total current that comes out from here is 8 ampere. So it's equals to the sum of current here. So this is 3 ampere, 1 ampere, total 4 ampere. Therefore, the current in IZ will be 4 ampere, right? Simple. Now, the resistance of resistor Z, that is even simpler because we know that this is 6 volt and this is 4 ampere. So we have the V, we have the current. We just find the R using V equals IR. So this is 6, this is 4, R. So R equals to 1.5 ohm. Okay, calculate the amount of energy transferred in resistor X in 15 minutes. So this is a trick here. So this is the time I need to convert it to seconds times 60. Okay, because this is a SI unit. Energy is given in joules, so everything needs to be in SI unit for this. Okay, so 15 times 60, it is 900. Okay, seconds. Okay, so how do you find energy? Now, energy equals to power times time. Correct? And it is only for resistor X, yeah? So we need to find the power in X. So it's equals to Ix Vx multiplied by T. Ix, if we look here, Ix is actually 3 ampere. Okay. Vx is actually 6. They all have the same voltage multiplied by 900 seconds. So I will get 16200 joules. Okay. Okay, piece of metal foil is attached to a metal rod as shown. The metal rod and metal foil contain negative charges that are free to move. So these are actually your electrons. Only electrons and negative charges can move. Protons cannot move. Take note. So they are free to move throughout the metal, and positive charges that are not free to move. So they are helping you. They are telling you that protons do not move. Metal rod and foil have no overall charge. So initially they are neutral. Okay. So now I bring a negatively charged plastic strip here. So what will happen over here? We initially have our plus and minus, right? Because it is initially at neutral. But when electrons, this negatively charged plastic comes near, the electrons will be repelled down. Electrons will be repelled, right? As light charges repel. So this is something that you need to write. Light charges repel, yeah? So when the electrons move down, it will move down to here and move down to here as well. And this negative charge plastic is held over here. Okay? So since the light charges repel again, there will be a force that will be exerted on the metal foil and cause it to move away from the metal rod. Okay, so this is the idea. So let's see how we can answer it. Okay, when a negatively charged plastic strip is held close to the top, the metal rod's electrons are repelled away to the bottom of the metal rod and metal foil, right? Because light charges repel. So then the electrons in the metal rod and the metal foil will repel each other, causing the foil to move away from the metal rod. So this is how you get your 2 marks. Okay, but students will also sometimes write about poles. This is only for magnets. Alright, so make sure you distinguish between magnets and poles. Okay, then question 10, it shows a type of thermostat that is used to switch off a fan when the temperature is low. Okay, so we have this mercury, and mercury actually conducts electricity. Okay, so if the contacts are here, it is a closed circuit, right? We have a power supply, there's a fuse, there's a fan. Okay, now the volume of liquid A changes by a large amount when the temperature changes. So this is a fact they're telling you. When the temperature changes, it will change by a large amount. It will expand. So mercury is a metal that's liquid at room temperature, and use kinetic theories to explain why a liquid has a fixed volume and is able to flow. We have to use kinetic theory. That means we have to talk about the particles. Okay, what happens between the particles? Okay, so they have attractive forces between the particles, attractive forces, and the molecules are held close together with little space between them. Okay, therefore it has a fixed volume, right? The particles are not free to move far apart from each other. Okay, but however, the particles are not held in fixed position, unlike your solid, right? So they are free to move, and therefore they can slide past one another. Okay, so this is how you should explain using kinetic particle theory. You must talk about the particles, not just the object itself. Okay, liquid A expands when it is heated. Let's see how we can answer this. Okay, when it is heated, the particles, again we have to talk about the particles, they gain kinetic energy and they move faster. Okay, so one thing that I didn't really emphasize to you all is that when we are talking about particles, we don't talk about their stores anymore. We talk directly about their kinetic energy and internal potential energy. So we don't need to talk about stores when we're looking at the particles. But when we're talking about the object itself, like liquid or this solid, we then talk about the store, like a ball, the arrow, you know, the bow. We talk about the energy stores. But for particles, we do not need to talk about the stores. We just say that it has high Ke or high potential energy. So for this case, when heated, the particles will gain kinetic energy and they'll move faster. Then they are able to move slightly apart from one another. So the volume actually increases when it is heated. Okay. So part B, they want us to explain why the fan switch off when the temperature is too low. Okay. So basically, they want us to explain the function of this. Okay, so why does the fan switch off? So you must, later on we'll look at the circuit, yeah, but let's look at the answer first. Okay, when the temperature decreases, liquid A's volume will decrease, right? They already told us that the volume will change by a large amount when the temperature changes. But of course, you know, as temperature increase, it will expand, right? So the volume will increase. Okay, so now when temperature decreases, the temperature is too low, so the volume will decrease. When it decreases, then my mercury will shift downward as well, right? It will shift downwards. When it shifts downwards, then possibly the contacts are not touching one another through the mercury. So the height of the mercury column drops. As mercury level falls, it loses connection with the upper point of contact with the wire and becomes an open circuit. So therefore, there's no more current and the fan will switch off, because they want us to explain why the fan switches off when the temperature is too low. Okay, part C calculation. It has a power 0.045 kilowatts, operates from 230 volts, so I have my P and my V. Suggests a possible fuse rating, which is actually the current value. So P equals to IV. So this is a kilowatt, so I need to multiply kilo. Okay, because I want my current, I don't want millicurrent or something like that. So I 230. Okay, so my current actually is 0.196 ampere. So what will be a suitable fuse rating? We can suggest something higher, like 0.25. Okay, how about 0.2? 0.20 ampere to me is a bit too low. Okay, or I can even suggest it to be 0.30 ampere. Okay, so something that is slightly higher, okay, but not just slightly. Okay, there must be some allowance. If not, the fuse will be melted, and then I have to keep replacing the fuse. Okay, so question 11, I think this one is a bit tough. The voltage of a power supply varies with time as shown in figure 11.1. Basically, the voltage changes direction. This upper part, it is positive. Then after 0.01 second, it becomes negative. Then it becomes positive, negative. Through every 0.01 seconds. They tell us that the direction changes every 0.01 second. So what does it mean? A coil of wire is wrapped around an iron core. Okay, so this is our power supply that changes direction and is connected to power supply P. An iron rod is suspended close to it. So iron rod, we take it that it is a magnetic material, but not a magnet yet, yeah? And a small bar magnet. So this is a bar magnet and this is our north. Okay, so power supply P is switched on. Explain why the iron rod is always attracted to the iron core. So I must also say that this is a soft magnetic material, so it's easy to magnetize and easy to demagnetize. Okay, so you must know this, because then we can use it to explain why iron rod is always attracted. Okay, so let me explain the iron rod first. Okay, as you can see, this is a 4-mark question, so I would expect like iron rod's explanation to be 2 marks. The magnet will be 2 marks as well. Okay, so let's talk about the iron rod first. When the power supply P is switched on, remember P, the voltage changes direction every time, so the current will change direction. And whenever there's current flow, okay, when current flows, it will produce a magnetic field. A magnetic field. So if my current keeps changing direction, my magnetic field will also keep changing its direction. So the current flowing in the coil of wire, the solenoid and the iron core is induced into an electromagnet. Okay, so as the direction of the current keeps changing, when the voltage direction changes every 0.01 seconds, take note here, the iron rod's end, where's the iron rods? This one. The rod end facing the bar magnet is induced with an alternating north and south pole. Okay. Okay, so this is actually talking about the bar magnet first, yeah. So because this direction keeps changing, maybe every 0.01 second it goes like that, then after that it changes direction. Then if you use your right hand grip rule, right, your north and south will keep changing direction. Okay, so for this bar magnet, every 0.01 seconds, here will be a north, so there will be repulsion as light poles repel. Light poles, so now you can use poles. Light poles repel. Then after 0.01 second, this becomes a south again. And because it's iron core, so it is a soft magnetic material, so it's easy to magnetize, easy to demagnetize. So the north and south will just be flipping very quickly, in fact every 0.01 seconds. Therefore, this small bar magnet will be looking at north for 0.101 seconds, then the next 0.01 seconds it will be looking at the south. So there will be attraction and repulsion. That is why the force on the bar magnet varies. There will be attraction, and then next there will be repulsion. Okay. For the iron rod, which is now this thing, because it is a magnetic material, it will become an induced magnet. This is important. Okay, if it's induced magnet, it will always be attracted. How is this so? If here is north, then he will be induced with a south pole on the iron rod. There will be attraction because because this is your magnetic induction. Okay, then when here becomes a south pole, it will then becomes a north pole. So there will always be attraction, a force of attraction, right? Therefore, the iron rod is always attracted to it. Okay. So they advise us for the iron rod need to explain clearly. It is magnetic material. It is an induced magnet. It is an induced magnet. Okay, so I want to emphasize this again. If here is a north pole of a magnet and this is a south pole, if I put a iron rod here, iron paper clip here, here will be induced with a south pole. Here will be induced with a north pole. Why? Because remember, the north, the magnetic field's direction comes out from the north. Okay, so it will cause the tiny magnets in the iron to face in this direction. Okay, but let's say now I switch it over, and here is north and south. Then this is my iron paper clip, and this is the south. So magnetic field direction will be directed into the south pole, which means here will be a north, here will be a south. Okay, they will follow the direction of the magnetic field lines. Okay, part B, the iron rod is removed and the bar magnet is attached to a cone of paper to make a simple loudspeaker. So no more iron rod. We still have this power supply which changes direction every 0.01 second, remember? So the magnet causes the paper cone to vibrate, right? Why so? Because here is a north, then it will be repulsion. Then next 0.01 second, it will become a south because the direction of the current changes. The direction of the magnetic field also changes. Here is a north, so here will be attraction. Okay, so when the cone vibrates, it will produce a sound wave in the air because this is air, right? So the surrounding air particles will be vibrated, will be push and pull, right? And pull. Okay, so use figure 11.1 on page 14 to calculate the frequency. Okay, I think I'll just copy the answer here because my stylus ran out of battery first time for me. Okay, so I'll just copy the answer here and use it to explain. Okay, figure 11.1, we know that the period is actually 0.02, right? This is a start, then end. So one whole period is 0.02. So period is 0.02. Frequency is 1 over period, so it's 50 Hertz. Okay, so because they want us to calculate the frequency, answer should be 50 Hertz. So now power supply P is now replaced with a second power supply that causes the speaker to produce a sound wave of frequency 240 Hertz. Just now it was 50 Hertz, now it's 240 Hertz. That means the frequency has increased. The speed of sound in air is 330 meter per second. Calculate the wavelength. So using V equals F lambda, I will get 1.38 meters. Okay. So this one you should get. Wow, it's a 3 marks. Very generous. Okay. So the new current in the coil is smaller than when power supply P was used. That means the new current is lesser and it's a different frequency. Describe and explain how sound produced with the second power supply is different from that. So if I have a smaller, let me bring this down. Okay. If I have a smaller current, what will happen? The magnetic field will be lesser, right? Because since the new current is smaller, the force of attraction and the repulsion on the bar magnet will be weaker. So this will produce smaller amplitude of vibration in the bar magnet. So the push and pull will be smaller. The magnitude of the push and pull will be smaller. So the sound will be softer. Okay. But now we have covered the amplitude, the loudness. But because now it's of a different frequency, the frequency is actually higher, 240 Hertz. So the frequency of the sound will be higher because the sound produced with the second power supply has also a higher pitch. Okay, so they tell us to explain the change that caused the specific effect. That means smaller current, smaller push and pull of the bar magnet, so smaller amplitude, therefore less loud. Okay, the sound is softer. So this is one part. The other part is about the frequency. The frequency is higher, therefore the pitch is higher. Okay, so this is unacceptable. Frequency is changed, so pitch is changed, because this is very vague, right? It can be that frequency increase but pitch decrease, but we know that that is wrong, right? So you have to be very explicit. The frequency is higher, so it has a higher pitch, right? You link directly to it. Okay, question 12 is a VT graph. So from A to F, it shows the car braking, colliding with another car, stopping, increasing speed at its greatest rate, stationary, but not in this order. So we have to use this phrase to talk about A to B. Okay, but before that, you need to know that velocity time graph, what is important? The gradient represents acceleration. Okay, and the area under the graph represents the distance traveled. So this may be quite new to you because the speed time graph or the velocity time graph actually goes below negative. Okay, but we'll talk about it later. We solve for A to F first. Okay, so let me show you the answer. Okay, from A to B, it is actually stationary, right? Because the velocity is 0. This is simple. So from B to C, actually it is velocity is increasing, and it seems like a straight line, so the gradient is constant. So it is increasing speed, but is it at its greatest rate? I think it is increasing speed at its greatest rate. Yeah, the speed is increasing at a greater rate because the gradient is steeper than CD. So CD is actually increasing speed. Okay, so the difference between B to C and C to D is because of the gradient. So a larger gradient means that the speed is increasing at a greater rate. Okay, then after that, D to E, what happens? D to E, is it braking or it collided with another car and stopping? Okay, so E to F will be stopping because F, the velocity becomes 0, right? So it must be stopping. So over here, it collided with another car and stopped. And D to E is actually braking because when you brake, the speed decreases. Okay, so this one should be quite okay. Then by considering the forces on the car, explain why the speed of the car decreases between D and E. D and E, Okay, so from D to E, we know that it is braking. Okay, we see on the graph, the speed decreases, it decelerates as there's a resultant force in the opposite direction of the car's motion. Right? This is because the braking force has increased and the braking force is greater than the forward driving force, right? So if you want to brake a car, make it stop, there must be a force that's exerted in the opposite direction of the engine force. Okay. Now they want us to describe the motion of the car between F and K. So F and K, okay, you see that actually it went below negative. But if you know about velocity, it is actually a vector quantity. So if it's a vector quantity, it has direction. So the plus and minus is used to show the direction. So if plus is, let's say, going to the right, then minus means it's going to the left. That's all. But from F to G is actually stationary because the velocity is 0. Then G to this point of negative 10, the speed is actually increasing, but it is moving in the opposite direction. It's increasing because the speed went from 0 to 10. But why in the opposite direction? Because it's negative, right? So it's opposite direction. Okay, so let me show you the answer. Okay, so from F to G is stationary. This one is quite easy. G to H, the car travels in the opposite direction. So that means as long as it's below the x-axis, where it goes down to the negative, it means it's in the opposite direction. Plus is in one direction, minus is in the opposite direction. So then you look at the number from 0 to 10, the speed is actually increasing, but it is going in the opposite direction. Then at this point, the speed is actually going from 10 back to 0. So it is reducing its speed. Okay, but it is still traveling in the same negative direction. So if positive is going to the right, all these are going to the right. Then once it reaches negative, that means it's going in the left position. That means it's going back. Okay, so G to H, the car travels in the opposite direction, starting with a speed increasing at a decreasing rate. Why decreasing rate? Because the gradient is decreasing, right? From steep to gentle. Okay, then the speed then increases at an increasing rate. Why is that increasing rate? Because the gradient goes from gentle to steep, right? If you put a ruler against it, you'll find that the gradient is increasing. Okay, then yeah, so H to J again stationary, J to K is the speed is increasing at a constant rate, and you see that it's actually positive in a positive portion of it, so therefore it is moving to the right again. If let's say just now we say positive is going to the right, yeah. So this question is quite tough, right? Because actually for combined science students, you don't really deal with velocity. So you might want to look at this question again just before your O-level exam. Please put a star in this question. Now they want us to calculate the average acceleration of the car between C and D. So now we have to go to C and D. We just find that the initial velocity at C, final velocity at D, what is the time duration, and we can find the acceleration. Okay, I'll show you the answer here. And that will be the last of this last question in this paper. Okay, so just make sure you check the timing, yeah. Okay, so this is all for 2015 paper.